Okay, let's continue because I think I missed something important also. Mm, the complex numbers. The way it was designed to work mathematically is that when you multiply two complex numbers, you add the angles. It will end up to the point in space where you add the angles together. So basically, here we have angle 0. If I put 90°, it will go there. So this one I is basically I is a notation to say 1 times I. But that means you just go on 1 on this other line that is um, vertical. And when I do multiply by I, that would add another 90°. So every time you multiply something by I, all you do is 90°, then 90°, then 90°, then 90°. So all you are doing is, so you go from real numbers but positive, then complex number positive, then real numbers but negative, and then imaginary number negative, and then back to real number positive by going around the circle, but by steps of 90°, right? You always end up on the line. So we have 4 patterns there, right? We have like positive, positive, complex. So let's write it down. You will have like real numbers, then followed by um, complex, followed by negative real, followed by negative complex, and then you loop around. That's what that means. You can think of that sum that goes to infinity as being like 4 stuff. It will always go real, complex, negative real, negative complex, and back. So in the end, you will only have like some real, some negative real, and when you put them together, they will give you this cosine. The complex, when put together, the complex, they will give you sine with I. That's why you have I in the end there. So how does it plays out? That means, let's take this one. We said when it's even, this, no, wait, it's not just even. It's just a pattern of here we can say this is 0, 1, 2, 3, right? So let's try to separate them. So the first one is real, plus the second is complex, so the x we discard. Then we have x power 2 over 2, but negative, right? We said it's negative. Then we skip another one because this is complex, but then we go back to real. So what happens, you would, let's divide it by, we said 24. You see, now let's put cosine of a. No, cosine of x. Just put cosine of x. You see these terms there? They converge. there are too many stuff around. Let's remove some stuff that we don't use anymore. So this one we don't care because whatever. So the green curve is our thing here, right? So we went from 0 to 4. Now we alternate. We have minus x. We skip the 5. It's 6 now. Oh, fuck. 6 divided by 2 times 3 times 4 times 5 times 6. You see it fits. It fits. And as you increase this sum, where we just gathered the positive, the real numbers from this infinite sum, we just gathered the real parts and we separated them from the complex part. And that just means keeping like a sum of the terms, right? Like we went from 0 to 2, we skipped the 1, then we skipped 3, then we skipped 5, and by doing this, it fits the cosine. And if we do the same, but for, so we start with x plus, so we said minus x3, the one that we skipped. So 2 times 3. I could have written like a 6, but whatever. And then plus x times x power, we skip 5, and we skip 4, so we get 5, and then we put 5 factorial, so I'm lazy as fuck. And now we will plot sinus. And let's disable those just for clarity. And you see that our black curve is slowly fitting sinus function. And this is the beauty of it. Like the exponential function, if you use complex numbers, would split into two sums, which would equal cosine. The real part would be cosine, and the other would be sine. Let's put not x but a as usual. It doesn't. And this is, and by definition, you already know that cosine of something is the projection of the I mean it's the cosine and sine are tightly bound to a circle, right? And this is the beauty of it. It's like it seems completely out of the blue, but this infinite sum, when using complex numbers, would almost magically fit split into a cosine and sine. It's beautiful. It's magnificent. I love this shit.